Right. The first thing that you have to do is to set your working space, set working WD, and set it to the place that you are working with your files. So I will set this one to the folder that I'm working, and it is done. So once you have done it, you can get WD, get the working directory, and it will show you where you are. And after that, what you need to do is to copy paste the codes with an initial idea of what you are doing. So the first one is to install all the required packages. So I will create a script first. So you have to create R script. I'm going to save it in the working folder. So now I'm there, and I would say R code assignment and save it. So the first thing that I'll do is I'll copy paste the install all the packages here, and with the dependencies being true. So I will also run it here so that I can show you if there are any dependencies or issues. You can see it being installed in my computer. Once you install these libraries, you can load them to your working environment. The next stage of the code is to change the available .geo columns stored in GeoJSON encoded point geometries to whatever that is useful for us. Because your data set contains .geoJSON, let me first of all load the CSV. I'm going to load the CSV to the working environment, and I'm going to store that as a DF data frame row. So I'm going to paste that code. Now you can see df underscore row 9994 observations have been imported or loaded to our working environment. You can check the structure of the data. You have NDVI, NDBI, and other parameters or features, and .geo format of the coordinates. So these are the coordinates that we need to change to our format. So let me save it before we go forward. I'm going to concatenate or collect everything into this. And you can see the dimensions and the number of rows and the columns. Right. Now I'm going to get a glimpse of the DF row, which is of course available in your code. Anyway, this will show you the available data and its other details, double format, character format, and other details. We have already seen this in our table. Now I'm going to create a longitudes and latitudes column. So let me create that. And I'm going to go through each entry point which is in the type of point coordinate. It looks like this. Type point coordinate. You can see somewhere here type point coordinate and the coordinate point. So I'm going to change that to creating a geo list of conversion from the GeoJSON and then I'm going to put that into longitudes and latitudes. So this one will add a longitude column to our row data frame, and the next code will create a latitude column. So now our data set will have 13 features because now it contains latitudes and longitudes, like this, longitudes and latitudes. Let me save this. Okay, now we need to create a data frame which is clean for the analysis. So I'm going to do that. Clean working data frame. Let me have some space here. Enters. And I'm going to create a data frame using a pipe command. This thing is called pipe command, so I'm going to use that. Now I have a new data frame without that geo column. So let's look at our results at this instance. So I'm going to print them. You can see missing values per column. You don't have any missing values. The data set is clean. And the next stage is creating a SF object, which is the spatial object for R. And we are going to create that using the coordinates with data frame with the spatial object coordinates, dfsf. And finally, we'll look at the available data like this. Right. Now you can see the minimum X, the minimum Y, and the bounding box particularly of that object. Okay, so we have pretty much completed the initial data import or the loading process in R. The next one is exploratory data analysis. We'll start with descriptive statistics. We will do a little, first of all, we will create index variables for the data. So I'll include that variable list for analysis. We will need the IDX values for all the variables. So I'm going to create that. This will create index variables for NDVI and all the way up to the emissivity, and all the variables, the LST, that is land surface temperatures, will be accompanied with that IDX variable, so that we have a clean set of values. Okay, let's look at the summary of the data for all variables. You can see clearly the land surface temperature, NDVI, NDBI, and all the other things very neatly. Now, for the demonstration purposes, I'm going to create a table via tidyverse. That is for particularly data science workflow in R is done using tidyverse. So I'll show you a neat table of what we get. So this has all the values like mean, standard deviation, minimum, medium, what we call 5-number summary that is available in this table. Okay, so I will just put a code there as well since it is available in the tutorial, and you can see that table right here. Excellent. Now let's look at the land surface distribution. First of all, I'm going to create a histogram of land surface temperatures with the mean line and the IQR. So in order to do that, I have to create the Q1, first quantile of the land surface temperature, Q1 LST. You can see the values Q1 LST here. So I will follow the same procedure for the Q3, IQR, and the fences, which are called as the anomalies that you find in data. So Q3 is the third quartile, and then you have the IQR interquartile range, and then interquartile minus 1 first quartile minus 1.5 times IQR. This will give you anomalies of the data. So I'm going to run that so that I have a nice bounding for the data that can be even used as a box plot, box and whisker plot. Let's see whether we can actually see that using the next command, which is the creation of a histogram. So I'm going to run this. All right. So first histogram, P1 histogram is available here. Here, large ggplot values are available. So I'm going to create that and look at it here. Okay. Now you can see very nicely the distribution of land surface temperature with the mean of 33.77, and it's a very nice distribution, a normal distribution with IQR with the outliers as well. So now I'm going to create a box plot. These are all exploratory analysis workflow. I'm going to create a box plot of all spectral indices, and in order to do that, I will just copy paste the code that I have shared with you in the assignment and enter. Now we can see the box plot for each and every variable available in our workflow. I will also do a Pearson correlation matrix to see whether there is a linear correlation between the variables. So I will just copy paste this, visualizing with correlation plot. Let's see what we get. Very nicely we can see all the details. Very nice. You can see the correlation plot for each and every variable in combinations, and you can come up with the insights that you want. Now I'm going to create a land surface temperature versus NDVI scatter plot. Scatter plot colored by albedo. So you can see multiple variables being included in this analysis. I have the land surface temperature, NDVI, and albedo. So I'm going to run that code here so that we can see multidimensional data, including LSD and the NDVI with the albedo. Let's see. Very nice. You can see NDVI on your x-axis, LSD on your y-axis, and you can see albedo colored very nicely. So you can see negative correlation with LSD on versus NDVI. Let's go forward and see what we have in the spatial visualizations. So our section 5 is about spatial visualization. And in order to do that, I'm going to create a reusable point map function that will be also available on the code. So map points visualization is there. And our next creation is a color ramp for individual maps. Right, so I'm going to use the color ramps here. You can see the colors even. Color ramps have been created, and I'm going to create individual maps for each one of the variables that were in concern: land surface temperature, NDVI, NDBI, and albedo. And all the maps are also named clearly. when we run it, the images will be saved under PLST, albedo, and other variables. Now we'll look at a multiple linear regression. Okay, so we will create a regression analysis and print the result. So I'm going to use that. I'm just going to copy paste that code here, right? And this will give us a regression, all the variables with the statistics. It's very nice. Right, so we'll look at the multi-collinearity check as well with the variance available. So the expectation is that we have EVI, SAVI, NDBI, and those pairs will produce high variance. The analysis will show us that. So let me show you the result. If you copy paste this code and there's a closure needed, and I'm going to run this code, you can see the variables very clearly. Now we will drop one from the highly correlated pairs in order to get a clear picture of what we are dealing with. So I'm now going to quickly do it so that you can also check what sort of an output you are going to get, right? So this is the output that you get in model comparison, full model AIC and reduced model AIC. So we'll look at the residual diagnostic as well with plots, standard 4-panel. So I'll just type in residual diagnostic, residual diagnostic. Excellent. So I'm going to directly copy paste the code here, and we will see the predicted observations clearly. So I'm going to run this. We have predicted LST and the observed LST using our regression analysis. So we can see the line and the data points that were predicted. Excellent. Now we will go to the spatial autocorrelation. So this is the spatial part of the work, spatial autocorrelation. And I'm going to use the global Morans index. You know that if it is the global autocorrelation that we are looking at, it will give us an idea of how the values are spreaded spatially, whether they have any autocorrelation for the nearby extent. So we work on reproducible subsample of 3000 points for the neighbor weight computations, because we don't have a lot of high-end computers, so I'm just trying to reduce this workflow. But if you have a higher RAM, you can actually go ahead with all the samples, the number of samples. So I'm going to create a subsample for spatial weight computation. So I'm going to give you that as a comment. So number of sample is 3000 to minimize the RAM usage. So I'm going to create this IDX sampling, the data frame. There's a little missing part here, right? So I'm going to run this. Excellent. So coordinates have been subsampled, and our first thing is k nearest neighbor spatial weights for k equals 8. That is our first thing. So I'm going to use KNN 8 and see what we get. Right. So I'm going to print the summary of our KNN clustering. So we can see the neighbor summary. You can see the neighborhood with the KNN clustering for 8 sample. Now I'm going to create the global Morans I on LST because that's the thing that we are interested in. Global Morans I on LST. Let me save this first. And I'm going to print the Moran LST once we create it. You can see Moran size statistics, expected value, and the variance have been shown. If you remember what we discussed about the Moran's index, you will see the clear picture here. So our next task is actually looking at the global Moran I on NDVI. So I'm going to use NDVI here. And I'm going to paste the code for the NDVI. All right. And the next one is NDBI. Moran's I for NDBI. NDBI. Okay. I'm going to copy paste that part as well. So you can also do it like it's very simple, just copy pasting the code. But the important thing is understanding what you do here. So I'm going to create that NDBI like this. Now I'm going to create the Moran's scatter plot for the land surface temperature, because land surface temperature is the thing that we are interested in the analysis. Land surface temperature. I'm creating the Moran.plot. Let's see what we get. Moran plot. And here we have it. The Moran's scatter plot. You can even zoom in to see the points in space. Interesting, right? And we'll move forward with the local Morans for the hotspot identification. So in the case of local Morans I, if you remember, what we try to do is to see how they are correlated locally. So I'm going to create that, and I'm just going to copy paste the code here, which you have, computing the local Moran's index. If you run this, you can see the hotspots being created, and we will create the local Moran's index like this. Right, so I'm going to copy paste the other part of the code once we create the color ramp for this. Okay, so I'm going to create the Lisa index for the, very nice. So you have the Lisa cluster, high, high, low, low, and not significant. So you can see the cool clusters and the hot clusters for Sri Lanka. Right. So the next one is creating the JETIS G-sharp hotspot analysis. So we have to first of all create the binary weights for this. All right. Creating the binary weights with the self-inclusion, which is required in the GI star JETIS or calculations. I'm a bit lazy to type everything, so I'm going to paste the code here and run it. You have the clustering, G star clusters with hotspot and the Lisa clustering. So this GI star is about the local clustering, where you have the variations of the anomalous clusters. So you can see high and low clustering there. So last but so as the section 10 of your handout, we'll talk about the spatial regression. Okay. So we'll look at the OLS residuals, whether they are spatially autocorrelated, guiding the choice between spatial lag model or spatial error model. I will directly copy the code back here. So to expedite the process. Now we got the final result for all the models, the regressions, and we will create a UHI composite index and intensity zoning as our last code. So I'm going to create UHI composite index and intensity zoning. Now you can see a very nice distribution of the UHI zone and the LST distribution, which basically tells us what is the distribution of the land surface temperature based on each of the UHI zone. If it is a very low zone, the temperature will be between maybe roughly around 20 to 25 maybe. But if it is a high zone, it goes up like that. So that is the idea of this UHI zoning. This is entirely for Sri Lanka. And now the export section, we will export the results so that we can use it in our research paper. This is how we export the results. So you have the code, you just need to copy paste and run it, and that will be saved. All the summary results will be saved here in the folder. So if I go to the folder now, GORS, you should see the results. Sri Lanka UHI, the data file is Sri Lanka UHI results. So I will just double click this and show you the result. So you can see all the results. Now what you need to do is to run this code and follow the rest of the work and creating that report, the research paper about the results that you see here. Hope this is clear.